Good afternoon to my peers, esteemed teachers, mentors, and principal. I, Rashmi Nair of MYP4A, am honored to introduce today's guest speaker, Dr. Sébastien Foucaud, an expert in the area of astrophysics who has made significant contributions in multiple fields. He earned his PhD in astrophysics from the University of Aix-Marseille in 2002 and has since made significant progress in the fields of observational cosmology and galaxy formation, publishing over 160 refereed articles in leading journals such as Science and Nature. Dr. Foucaud has worked as a professor in multiple countries such as Taiwan, China, Germany, and currently India. He has led the development of 2 major astronomical data centers collecting petabytes of data from ground and space telescopes, which have been made available to the global scientific community. He's now based in Germany, working in the field of data science and artificial intelligence. Currently, Dr. Foucaud serves as an adjunct professor in data science and AI at Plaksha University in Punjab, where he lectures graduate students. Please join me in welcoming Dr. Foucaud on stage.
This one? Hello. Okay, thank you very much for the invitation. It's a pleasure to be here today and see this large crowd of students and faculties. Thank you very much. So actually, I'm not living in Berlin anymore. I just transitioned to Greater Noida since a month now, living here in India. I'm very acquainted with India and Indian culture for years. Hello, sir. Being married with an Indian woman for 16 years. And it's my pleasure today to talk about one of my, let's say, lifelong passion, which is astrophysics. And we're going to talk in particular about cosmology and galaxies. So that's what I've been doing for almost 15 years. The day of today, I'm not in the field of astrophysics anymore. I left the field around 10 years ago and transitions from galaxies to data. And I will explain to you during the lecture today why basically data is so important for me. And for the past 10 years, I've been in the field of data science and artificial intelligence. I won't have time today to talk about it, but hopefully we'll have another opportunity to discuss about the other part of my passions for life, which is basically artificial intelligence and machine learning. I am, as mentioned, adjunct professor at the Plaksha University, which has some connections with Prometheus. I'm going there on regular basis. It's in Mohali in Punjab, next to Chandigarh. But my main job today is around data science and artificial intelligence. I am a consultant. I'm advising companies worldwide, mostly in the US and the UK and Europe, around their strategy around data and artificial intelligence. And I'm also running what we call technical due diligences, which is essentially evaluating startups, companies in the field of technology, in particular in AI, on behalf of venture capital companies and private equity firms. So when people want to invest in the company, they call people like me, and I can assess what is the technology that the company is using. So this is my main job today, but I always kept a stream with astronomy. I always basically I'm in communications with my former colleagues, and today we're going to talk about cosmology. So this is a picture of me with a little bit more hair. That was back in 2010 or 2011. This is La Silla site. It's in Chile, in North Chile, in South America. And it's one of the numerous sites where we have telescopes. It's at around 3,000 meters of altitude. And these are different telescopes. The one that's a bit squarish that you see at the end of the road. Is there a pointer in this? Here. It's called the New Technology Telescope. It's an optical infrared telescope. And I'm on the top of another telescope called the 360 telescope. And I was there for conducting observations on basically galaxies. I've been doing to this type of sites in Hawaii, in Chile, in what's the name of it? Gran Canaria Islands, and for many, many times. I was going probably 3 to 5 times per year in Hawaii for a period of my life. Only astronomers, you will only hear astronomers saying like, oh, I have to go to Hawaii again. Okay, so this is the same picture, and this is basically showing you different places where I lived throughout my life. So I'm French originally. I spent most of my life, or half of my life so far, in France. And after graduating my PhD, I lived in different countries, including Italy, UK, Taiwan, China, and Germany. I spent extensive visits in Japan and the US as well. I was a professor at the Shanghai Jiaotong University. That was my last tenure in Shanghai, where I was basically teaching astrophysics and running my research. And around 10 years ago, as I mentioned, I transitioned away from astronomy, and then I've been working for many different companies as a chief data officer and chief AI officer, based in Germany mostly. And now for the past 3-4 years, I'm exclusively focusing on consulting. So in 1995, I was basically doing my master in physics, and this picture has been published. So it's a very famous picture taken with the Hubble Space Telescope. And what they did is they took this telescope, I will talk about it a bit more, and they just decided to point it at a place where we knew we couldn't see anything yet. So it's a dark spot in the sky. You can see here the square here showing you the size compared to the size of the moon. Okay, so this is what is observed. And at the time, we couldn't see any light with the technology we had at this time. So nothing to be seen. And after 10 hours of observation, so they pointed out to this part of the sky for 10 hours, this is the picture that comes out. So apart from a few stars, I think there's 1 or 2 stars in here and here, all the points, light points that you see on this picture are actually galaxies. There are around 3,000 of them, and some are nearby, and some are very, very distant from us. Okay, and that's essentially what reinforced my passion. And when I saw this picture for the first time, I said, okay, I always wanted to do astrophysics, but I knew that I'm going to dedicate my career on this type of pictures. I wanted to understand where those galaxies are from, how they are formed, how they evolve. So 3,000 galaxies, that seems a lot, actually a lot more out there. So what are galaxies? So galaxies are an ensemble of stars. They compose of billions and billions of stars. And they also have a lot of gas in there and dust. And it's actually complex ecosystem where those 3 components are constantly interacting to each other. Everything here is bound by gravity. So gravity is putting all that together. And there are many, many forms and shapes of galaxies out there. So this is called M. Messier 104. It's a catalog of galaxies. It's not a galaxy that is too far away from us, only several hundreds of thousands of light years away. This galaxy is seen by the side. Okay, so you see the dark patch in the middle. It's just showing you that the light that is emitted from the stars from within the galaxies is absorbed by dust. So it's called the Sombrero galaxies as well. It has a nickname. This is another type of galaxy, what we call elliptical galaxy. It's way bigger than the previous one. And it's basically this halo-ish spheroidal shape. And it's composed, again, of billions and billions of stars. Galaxies have their own life. Okay, they evolve like everything in the universe. They're born, they evolve, change, and eventually die. And one way for galaxies to evolve and change is by interaction. All right, so essentially this is called the mice. It's 2 galaxies that are colliding to each other. All right, so it's a very slow pace at our time scale. But basically those galaxies are turning to each other, dancing a little bit, collapsing. And what you see, those big strips of stars, it's actually what we call tidal waves. So if doing the interaction, there are stars and gas and dust that are stripped away from one galaxy and then ejected in the surrounding space. Eventually, those 2 galaxies will merge and form a bigger galaxy. And sometimes you may have interaction with many of galaxies together. Like in this case, it's called a Stephan's quintet. There are 5 galaxies in this picture, and you can see again that 2 are merging here, and this one are interacting. Those beautiful like galaxies here that we call spiral galaxies, All right, so this one is seen from the face. This is exactly the shape of our galaxies that we call the Milky Way. So the Sun is in one galaxy, and the galaxy is called the Milky Way, and it's a 4-armed spiral galaxy. It looks very much like this one. So I mentioned the Hubble Space Telescope, and everything starts with that. To observe those galaxies and understand how they change and how the universe grows, we need to be able to use technology. Technology is so fundamental to science in general and astrophysics in particular. So the Hubble Space Telescope was launched in 1990, right? So when it took this picture I showed before, it was 5 years in space. It's around 700 kilometers orbiting around the Earth. It's not very high. It's more or less the same height where the space station here. I will talk later on about the JWST, so the James Webb Space Telescope, which is the replacement of the Hubble. It's several million kilometers away from us. So the Hubble Space Telescope is pretty close to us, and it's still in operation. It's still active, so we still use it to collect some pictures. And it's named after a very famous astronomer, physicist called Hubble. So I'm going to shift now, because one thing that I would like to discuss with you, and the title of the lecture was Decoding the Universe, is that actually what I've been doing throughout my whole career was to use galaxies, not to understand the galaxies themselves individually, but to understand how together they are changing and how the universe globally is evolving. And Hubble is actually a very, very important person when it's about what we call observational cosmology, so the study of the evolution of the universe. So this sir, Edwin Hubble, an American astronomer from a century ago, was using different telescopes from the ground. So it's called the captivate telescope. He was using here on the Palomar telescopes. And one thing that he was very interested in was trying to understand how distant those galaxies were. At this time, late 19th century, early 20th century, we didn't know if galaxies were part of our universe, our galaxy, or if they were a distant object further than that. And Hubble was one of the person that allows us to understand that galaxies are not close by like stars, but they're actually extremely more distant. And they are so distant that actually we can see galaxies today that are billion light years away from us. And why it's interesting is because I'll come back on that in a minute. But it's interesting because if you look at a galaxy that is 1 billion light years away from us, you see it as it was 1 billion years ago. So somehow with cosmology and with this type of telescopes, we have the ability to go back in time and to look at the universe how it was a very long time ago. A little bit like, opening books and pictures from your forefathers and before. You can have pictures of how it was 100 years ago. Here we're talking about pictures of how the universe was billion years ago. And all rely on one very important principle in physics, which is called the Doppler effect. And I know that in MYP4, you looked at it very recently. So the Doppler effect is something that we are all very familiar with on everyday life. When you walk on the sidewalk of a street and you're overtaken by a motorbike or a car, you will see that the sound is actually changing. It's doing something like meow when it goes very fast away from you. The actual sound emitted by that particular car is always the same. When you're inside the car, the sound is constant, it's exactly the same pitch. But because of the difference of velocities between yourself, standing still or walking more slowly than the vehicle, then the pitch of the sound will change. Somehow, it will be higher pitch when it's moving towards you and lower pitch when it's moving away from you. And this property of sound is the same for any, basically, waves, including light. So the Doppler effect applied to light. So if you have an object moving very fast towards you, it's actually going bluer because the wavelength is getting shorter, higher pitch. And when it's moving away from you, it's getting redder, lower pitch, right? So longer wavelength. And these very basic properties of waves is actually extremely useful for astronomy because we can use that to actually measure the speed at which galaxies are moving away from us or moving towards us. And that's one of the properties that Hubble used to basically understand the evolution of the universe. So these are spectra of galaxies. So essentially, when you take the light and you put it in a small slit, you diffract the light, and you will end up to have what we call a spectrum. So it's basically as a function of the wavelength of the light. And those spikes that you see are actually emission for a given element. So when you look at anything around us, including ourselves, we're composed of atoms, and each atoms are basically a spectral signature. So we know that, for instance, hydrogen will emit an emission line at a particular wavelength. The same with oxygen, the same with carbon, etc., etc. So when you basically diffract the light, you will see this type of spectrum, and you will know what are the elements that is composing the source of the light. It works with the sun as well, right? And in this case, you will see it's different galaxies. And here you have a helium line. This line is emitted by helium. And essentially, what you see is that those galaxies are moving to the red. So this one is closer, is moving away slower than this one that is moving away faster from us. As a result of which, you see that this emission line is actually moving to the red. That's what we call the redshift for galaxies. So essentially, we have the ability, by just observing an object, a galaxy or even a star, to understand if it's moving away from us or moving towards us, and also to know how fast it's moving away from us. All right? And the second element that is important now to be able to measure the distance of galaxies is that you need to know how far away it is, right? You know how fast it's moving away, but how far away it is. And for that, we're using particular object that we call standard candles. So what are standard candles? They are objects for which we know intrinsically what is the amount of light, what is the luminosity of this object, independent of how far it is, right? So we know, like for instance, you take a light bulb at 400 watts, you know how many lumens is emitted by this light bulb. If you put it 100 meters away from you, you know how much light you will receive. It's basically just a proportionate of the inverse square of the distance. So the further the object is, the dimmer it will look to you. All right? So if you know how much light has been emitted at the first, and if you measure the light that you receive, then you can estimate the distance. All right? So standard candles are very important. You need to have those objects for which you know exactly how much light they emit at rest, so when they are close to you. And then if you measure how much light you receive, then you can derive the distance. And there are few, but several of those objects out there in the universe that you can use. One of them is called Cepheids. Cepheids are stars that are actually pulsating. They're changing in size, because of different properties. Don't have time to enter into those details. But those stars are essentially vibrating. So they are inflating and contracting, and inflating and contracting. And when they do that, when they are bigger, they emit more light, and when they're smaller, they emit less light. So we see these periodicities of light luminosity of those stars. And we know them very well. And we study them in our own galaxy. Now, the period at which the star is pulsating tells us exactly how luminous it is. So we know that if it goes fast, the intrinsic luminosity of the object would be smaller, and if it goes bigger, the intrinsic luminosity of the object would be larger. And we have that measured. So we really, really have benchmarked it in the local universe, so we know exactly those properties. So now we have something interesting, because if we manage to detect this particular object and measure the change of luminosity, then we know how much light it has been emitted. Okay? So what Hubble did is essentially, it looked for this type of stars in other galaxies. He looked for Cepheid stars in other galaxies that are not too far away, that they can basically resolve. And when he does that, by measuring the period of the star, he knows how far the galaxy it is. And meanwhile, he'll take the spectrum of the galaxy, and then he knows the velocity at which this galaxy is moving away from us. And it's called the Hubble law. So the Hubble law is essentially measuring the distance. So in astronomy, we're using parsecs around, it's basically 3 parsecs is around a light year. And on the y-axis, it's the velocity at which, the redshift essentially, the velocity at which the galaxy is moving away from us. So here you have 2 fundamental properties. Is distance a function of redshift? And as you can see, this is somehow a linear relationship. This was groundbreaking discovery for our ability to understand the universe, because now we have a way to measure the distance of objects, galaxies. We have the ability, by just observing the redshift, to convert that into a distance. And we can start suddenly map the universe around us, because we have this 2-dimension projected on the sky, plus the ability to understand the distance of the objects. And what Hubble discovered is that, at one exception, which is the Andromeda galaxy that is moving towards us, every single galaxy that is in the sky is moving away from us. All of them but one. And more importantly, because now it has the ability to measure distance and velocity, the further the galaxy is, the faster it's moving away from us. Let me repeat that. The further the galaxy is, the faster it moves away from us. So essentially, if you look around you, the universe is expanding. Right? Every object that is around you is moving away from you, and the further it is, the faster it moves. So think of that a bit. What does that mean? Let's say you're in a galaxy, this galaxy A, and you look around you, and you look all those nice galaxies around you, and then essentially what you see is this expansion. So every galaxy that you will see on the different line of sight is actually going to move away from you. And the further they are, the faster they're moving away from you. Let's change vantage point. Let's look at galaxy B. Well, you will get exactly the same thing. Right? Which is crazy. That means that the universe is expanding everywhere you are in the universe. Everything is expanding. The universe as such is expanding. So think about it 2 seconds. Imagine that you're on the motorway, okay? And you have a car in front of you, and a car behind you, and a car in front of the car in front of you, and a car in the car behind you. You're moving at a certain speed that you don't know. What you know is that the car in front of you is moving 10 kilometers away from you and moving 10 kilometers per hour faster than you. And the car in front of it is 20 kilometers away and moving 20 kilometers per hour faster than you. If you change your vantage point to the car in front of you, so I'm here in this car and I move to that car, all right? If I look back, the car where I was before, because I'm moving 10 kilometers faster away from you, I see this car moving away from me by 10 kilometers. It's 10 kilometers away from me and moving away from me by 10 kilometers per hour. So that's exactly what we see at stake here. Because everything is moving away from each other, independently where you are in the universe, you will always see the same expansion. It's a fundamental property of our universe, according to Hubble. Is that clear? So these drag very important properties, very simple observations, drag extremely important properties of our universe, right? So everywhere you look at, you see the same expansion. That means also that there's no center of the universe, because wherever you are, you will see everything moving. It means that this universe is actually infinite. That also tell you that the universe, with time passing, will be emptier and emptier, because everything is moving away. So things that were close to each other are going to be further and further away from each other. And if you reverse the story, that means that in the past, the universe was smaller, denser. So all the objects in the universe were closer to each other, right? And if you play the movie back to the start, then you have what we call the Big Bang. Because essentially, at some point in the history of the universe, everything was at the same place. So that's a completely change of the way of understanding of the physics that happened in the early 20th century. Like suddenly, thanks to Hubble, we were able to basically, we were in the need of an entire new type of physics to understand this universe. Any idea who's the person that is very famous to draw this new type of physics? Who is the physicist from the 20th century that came up with a completely different concept of the universe? Any name? You know this guy? Albert Einstein. All right? So Albert Einstein is one of the foundational forefather of modern physics. We had many centuries ago a guy called Newton, and we had then Einstein. Essentially, two of the most important or groundbreaking physicists that we had in history. So Einstein was born in 1879 and died in 1955. He's German originally, also he changed nationalities many times, and he passed away in the US. He was a professor at Princeton University, worked very closely with the Department of Physics there, of Astrophysics there. He did several very important theoretical discovery. Einstein was a mathematician and physicist. He was not an observer. He was not going to the telescopes. And there are many different things that he discovered, but there are three very important ones. The first one is called, and he drew that in 1905, it's called the special theory of relativity. And in a very, very short 2 words, it's just what he discovered is that actually, when you go to the very large scales, space and time are interconnected. At our scale, okay, time seems linear. You're just passing, and you have control on the space, but you don't have control on the time. But at the scale of the universe, Einstein demonstrated that actually space and time are interconnected. They basically draw changes towards each other. That was a very fundamental, important discovery. The next one, which is the energy mass equivalence, and it's very famous with this equation that you all have seen, E equals mc squared. Energy is a function of the mass times to the square of the speed of light, E equals mc squared. It's basically telling you that energy and mass are two aspects of the same thing, right? And you know that because if you factor and you move at the same speed, if I bump into one of you, the energy that I'm emitting, because I'm always 100 kg, will be a lot stronger than the energy that you're going to emit, and you're going to fly away, all right? I'm used to play rugby, so I can tell you can fly. Okay, so this is the second property of the universe drawn by Einstein. And then the last one that he put together, those two concepts in 1915, is the general theory of relativity, which was the theory used to basically understand our universe, all right? So when you're mixing space-time, energy, and matter together. So what this general relativity is telling us is that actually mass tells space-time how to behave. So if you remember Newton, when you have two bodies that are attracted to each other by gravity, they start to basically rotating. So the moon is turning around the Earth because actually it's constantly falling, all right? And due to the gravitational laws, it starts rotating around us. So the understanding is that there is some ways that those forces, gravitational forces, are transferred from one body to another. Einstein said, yes, but no. Actually, what happens is not that there are gravitational forces. What you see is actually the impact of the fact that the Earth is transforming the space around it. Because it has a mass, it's basically changing the space-time, and the moon is trapped into this gravitational potential. Exactly at this drawing here, which is a representation, that's not really the reality because you cannot represent 4 dimensions into a plan, but essentially the Earth is deforming the space around it, and every object that is lighter than the Earth is trapped into this deformation and start basically rotating around the Earth. So in one hand, the mass tells the space how to curve, and the other hand, of course, the space tells the mass how to move. And we have tremendous amount of evidences of that to be true today, right? The first one was discovered as soon as 1919, but today we have a beam of evidences that actually the general relativity holds. So this is it in equation. This is a very, very complex equation normally, and Einstein managed to simplify that. He was very good in communication. But to draw to this type of mathematics that is behind it, you need a master and a PhD. But what this equation is telling us is on the left-hand side, this is the geometry of the universe, so it's basically representing the space-time. And the other side, we have a matter of energy. And it's basically, as I just described, matter, energy, and space-time are related to each other. So thanks to the telescopes today, we can look backwards into through times. And we know that the most distant galaxies is 13.3 billion light years away from us due to the redshift. You have 5 minutes? Okay. Any other questions? Yeah. And so I mentioned briefly that we need telescopes, right? And I've been a user of telescopes throughout all my career. And we know how today have a next generation of telescopes. So these are the telescopes that I used to use. These are the telescopes that we build today. So this is the James Webb Space Telescopes. It's already in operation. Just look at the size. The Hubble Space Telescope, the mirror was 1.20 meters. It was that big. This is the size of the new Space Telescope, right? You see people there. It's 8 meters in diameter. And that thing has been launched in space. Okay? And it's taking amazing pictures today. On the ground, we also scale up, right? We are building bigger and bigger telescopes. This is an example. It's called the Extremely Large Telescope. It's built in Chile. The mirror is 30 meters of diameter. It's bigger than that room. Look at the building that they had to build for that. This is a car here, right? It's like a 5-story building. And this is in construction as we speak, so it's still not operational. This is the site in Chile, and it's an actual picture. And in other wavelengths, like radio, we have, for instance, the square kilometer array that is in construction in South Africa. So this will be a 1 kilometer by 1 kilometer array composed of several thousands of those antennas that you see here. And that thing is going to produce data. So essentially, when you observe the universe out there, you transform that into digital signal, into data. And SKA is going to produce 8 terabytes of data per second. I don't know if you understand the scale of what I'm talking about. 8 terabytes. What is the size of your phone in terms of memory? Gigabytes, right? So 1 terabyte is already 1,000 gigabytes. Every second, it's 8,000 gigabytes. If you start thinking about what that means at the scale of a day, it's 700 petabytes per day. Petabytes here, this is a representation. If you take hard drives and stack them up together on top of each other, to reach 10 petabytes, you will have a tower of hard drives of 3 kilometers high, higher than the Burj Khalifa, right? So 700 petabytes, that means it's 80 kilometers up to the mesosphere of disks stacked up to each other. And that per day, right? 80 kilometers, a plane flies at 10 kilometers, right? This is the amount of data the telescopes are producing today. And for that, we need data centers. And that's what I've been doing most of my career in astrophysics, right? Building up data centers to store this information. And that led basically me to become a data scientist, but that's a different story. Thank you very much.
As we begin with the Q&A session, I would request you to stand at your place and ask your question to our esteemed guest as your name is called. The first question is by Saranya Singh of AS level, but as she's absent today, I request Avril of MYP4 to please stand up and ask the question on screen.
Hi. What do you believe is the most significant unanswered question in astronomy today, and why?
All right. I need half an hour to answer that. I'm okay, thank you. So I dropped this picture very rapidly, but one of the things that we discovered in the past 10 years is that not only the universe is expanding, but it's actually expanding faster than what we believe, and it's accelerating, right? And if you look at the equations of Einstein that I showed before, that means that there's energy coming from somewhere that is making, it's exactly the fuel that you have in your car, right? So you need to bring in energy into the universe for it to accelerate faster and faster. It's what we call the dark energy. And we have, again, many evidences that to be the case, but we have no understanding or no comprehension of what dark energy is. So that's probably one of the biggest questions that we're asking ourselves. The other one is that if you look at galaxies today, and if you look at, basically, I explained that you can measure rotation. So you take this galaxy and you measure the rotation, the speed of rotation of the stars around the center of the galaxies, you can estimate the mass of the galaxy, right? It's just pure gravitational. So when you do that, you realize that compared to the light it has, there's a lot more mass. So the galaxies are actually rotating faster, spinning faster than the amount of stars that they have inside. And we don't understand where this extra mass is coming from. And we are talking about 80% of the mass of the galaxies that is unaccounted for. So it's called the dark matter. So we put dark there because we have no understanding of what it is. You know, it's the physics that we don't understand yet today. So the two main question astronomers, in my sense, need to answer, and physicists for the next 50 years, is what are dark energy, what are dark matter.
Next, I'd like to call Vivan Garg of MYP1B.
So relativity is definitely not a fiction. we have tremendous evidences of it to be a reality. As simple as that, there's an experiment that we have been doing now for several decades. You take a clock, right? A very, very precise clock. The most precise clock that we have is called atomic clock. Essentially, an atom is changing in state. And we know exactly the physics that's happening there, so we know very precisely what is the time, all right? So you take this clock at the ground floor, and you take the clock at the top of a very high building, and what you realize is that after some time, those clocks will grow async. They're not in sync anymore. But actually, it's what happens is that when you go on the ground floor, the time flies faster, physically, right? Even at the scale of the Earth. So we have many evidences of that. This is one of them. I can, again, draw a very large of them. One very interesting part, and if you haven't seen the movie called Interstellar, I really, really recommend you. It's a very good movie. And when you go to what we call black holes, which has very dense objects in the universe that are usually happening after the death of the star, and you go close to that black holes, that basically the time is going slower and slower. And it's very well depicted in the movie, what are the impact of it.
Third up is Nihal Tyagi of AS Level.
Good afternoon, sir. My question is, where does dark matter fit into the greater scheme of things? Like, what does it do, how does it work, and why was this theory created? And how does it affect our current understanding of the universe?
Right. So I answered partially to that already. I mean, incidentally, there was a large part of my work doing in research was around dark matter. Because, as I mentioned, if you observe a galaxy, we realize that 70% or 80% of the mass is unaccounted for. At the start, people were trying to modify the theory of Newton, gravitational theories, to account for that. But the reality is that even at larger scales, we see that. And the day of today, what I was looking at, what I was interested in, it was the formation of what we call the ground structures in the universe, or large structures. Galaxies tends to be gathering around structures in the universe that look like filaments at very large scales. And there are big places where we don't have galaxies. So we have been mapping that for decades. And we cannot reproduce that in computers without adding extra mass, which is basically the dark matter. Now, from a physics perspective, my colleagues in particle physics are very interested about that too, because, and I don't have time to talk about supersymmetry, but we know that when you look at very, very small part of the particles, there's also mass that we would like to account for. We know that there are many more particles in the universe than what we have detected so far. And the reason is because they are very exotic particles, so they don't have normal signature like light emissions, etc. So it's very difficult to detect them. And particle physicists are very interested in dark matter as well, because they think that there could be some of those particles that we haven't discovered yet, but they know that they are there to be a dark matter. So it has an impact on the very large and the very, very, very tiny.
Fourth up is Julian of MYP4. Please stand up and ask your question.
So, have you always wanted to be an astronomer since you were a young child? Or is this a job that you discovered later in life, like when you were a bit older?
As far as I can remember, and my parents can account for that, I always wanted to be an astronomer. I think I had my first telescopes, but my grandfather offered me my first telescopes. I was 6 or 7 years old. I have an anecdote actually. So after my high school, I went to studying math for a period of time, because I've been told that it was the right way and it was the wrong. And during those studies, I had a professor in physics, and he told me, "You're not good in physics enough. You will never be an astronomer." And years later, I had graded a PhD, and then I made a career out of it. So he was definitely wrong. So don't listen to dream killers. Just follow your passion.
Next up is Nirvana Chadha of MYP5.
What are your opinions on astrology, and can the positions of the stars depict how your life will go?
I've been asked these questions for so many times. When I introduce myself to people that don't know me, and I say I'm an astronomer, let's say a quarter of the time they tell me, "Oh, I'm a Virgo. What does that tell about me? What do you know that tells about me?" And I was like, "I have no clue." So from a physics perspective, no, there's no impact of planets on Earth on daily basis. They are too far away, so they don't have any influence. So that's definitely not a scientific fact. That said, beliefs are important in life. And if it helps you taking decisions on your day by day, and if you want to basically follow some principles of life that are related to astrology, there's no problem with that. My wife loves astrology because in India, that means that you need to buy her jewels, right? So she had rings in different stones, and then she believes very strongly in astrology when it's about to go to the jewelries. But apart from that, from a physics perspective, we have no evidences that planets have any influence on us. Stars do. The sun is, so every day you see it, and we are here because of thanks to the sun, but planets very little.
Finally, I'd like to ask a question. What is your advice for students looking to pursue a career in astronomy, and what career options are available in this field?
Oh, that's you. Sorry, I was waiting for someone to ask the question. Okay, that's physics essentially. So you need to go for physics. It's pretty heavy in math to be able to understand the theory. But nowadays, like every field, it's getting more and more broader. So I had to learn computer science a lot. I built, draw, and data centers, and most of my work today is related with computer science and data science. So there are many different aspects. If you're interested in the field of astrophysics, there is the theoretical aspects for which you need to study physics. There is the observational aspects, but there's all the technology that is surrounding astronomy, right? Build-up of telescopes. Any optical engineers, electronic engineers, mechanical engineers, space telescopes will require space science, etc. And computer science in particular is getting more and more important. Everything is about data, everything is about bits and software. So these are the different paths. But if you really want to pursue a career in astrophysics and theoretical part, that's physics you need to go for.
Now I'd like to invite Mr. Abraham to present the vote token of gratitude to Dr. Foucaud.
Dr. Foucaud, it's been such an honor and privilege to have you. When I was in school, physics was one of the most disliked subject for me personally, because I thought it was too complex. But listening to you for the last 45 minutes has been an absolute delight. I think the two fascinating areas that people talk about exploration is under the sea and in space. And what you talked about was very complex, but you made it so lucid and clear for all of us. Thank you so much. And I really loved your sense of humor and at the same time, being able to respond so well to those questions that were brought about. Thank you so much for an absolutely delightful afternoon of conversation. I know that some of the younger students probably didn't connect to everything, but I'm sure you captured a lot of ideas, and I really hope, sometimes we think that if I'm a student who's studying economics and, political science, what has this got to do with me? But remember something, there's no knowledge that is a waste. If you choose to, and as a student of international curriculum, you make connections through whatever you listen to, whatever you hear. So thank you so much. I also heard that he played rugby, right? Am I right?
I used to.
Yes. So what I'm also going to connect and say is that don't think that people who are all academics have never played sport, right? And vice versa. You can do both equally well. And that's what a school like Prometheus encourages you to be able to, develop your all-round skills. So thank you so much. And I request Mr. Sharma to kindly please come up and present this as a token of our gratitude for being here. A small gift. Thank you so much, Professor.
Mr. Sharma, would you like to tell the students to stay back? Okay. Students will want you to stay back. There is